So this is lecture number 12. So today we'll start with a new topic, a new equation. So till now the previous equation we solved was the 1D transient heat conduction equation. Okay, so now what we'll do is we'll make it 2 dimensions in space. So this becomes a 2D heat conduction equation which is transient. Because one spatial dimension simplifies many things, but here we want to see what happens if you have 2 spatial dimensions. And again, I mean, to extrapolate further, you can make it 3 spatial dimensions as well, but the idea would remain the same. So the governing differential equation in this case gets modified slightly. So if we recall the common form, so in this case we have the transient term del theta by del t, and we have the diffusive term which is the Laplacian of theta. So since we have 2 spatial dimensions, so del square phi becomes del 2 phi by del x2 plus del 2 phi by del y2. Okay. Right. So to make it well posed, we also need boundary conditions. So for that we have to define the domain. Now in 1 dimension, spatial dimension, it was just a line, but in 2 dimensions it could be something, some closed body in 2 dimensions. So let's define it. We'll keep it simple for now. You can make it more complicated if needed, but for now let's keep it simple. So it's a simple square of 1 by 1 size in x and y directions. So it could be any size in x and y direction, it could be rectangle, it could be a circle, it could be any closed figure for that matter. So you can think of it as a physical 2-dimensional body. So let's say a cooking pan, which is almost like a thin 2-dimensional body. So in that case it could be a square, it could be a rectangle, it could be any shape. Okay. So we'll need boundary conditions. Boundary conditions would be needed on the left, right, bottom and top boundaries. So the left boundary is given as x equal to 0 boundary. The right boundary would be x equal to 1. The bottom boundary would be y equal to 0, and the top boundary would be y equal to 1. I have not specified the values because different kinds of boundary conditions are possible in this case. So I am just letting you know that these are the boundaries where we need some conditions to make it well posed. And we will need initial condition as well, that is the value of theta at all x and y values at t equal to 0. So with these information, it should be a well posed problem. So now we have the equation, we have the boundary condition and initial condition. So now the next thing is to, in finite difference method, is to write the discretization or the discretized equations. So let's write the forward time center space first, the explicit discretization. It's very similar to the one we had written in one dimension, so just an extrapolation of that, except that now spatially we have to have an indexing to locate a spatial grid point. So if I define a grid structure like this, so you can see that now I have two spatial indices, one in the x direction, one in the y direction. Earlier we had only one spatial index. So we will use I for the I direction, x direction, and j for the y direction. So then what will happen is that a point will have coordinates I comma j, right. So you can, if I give you the I comma j coordinates or indices of any point on the two dimensional grid, now you can find the corresponding x and y dimensions, x and y distances. So x would be, considering it's a homogeneous mesh for now, delta x is the same and delta y is the same throughout. So the x coordinate would be I times delta x and y coordinate would be j times delta y. Okay. So we will use this indexing I comma j. So theta will be defined for each spatial node here. So theta will have to be defined for I comma j. Earlier we only had theta at a given I because it was a one dimensional problem in space. Now since we have a 2D problem, we will have to define theta at an I comma j index or a I comma j point. So since it is explicit, a forward time and center space, so on the right hand side all thetas will be at the nth time, and since the first one is derivative in x direction, so what that means is, and its center in x direction, so we will have to use points which are one point to the left and one is I comma j and one is to the right to calculate the derivative in the x direction. Similarly, for calculating the derivative in the y direction, we need one point above and one point below. Is that clear? It's very similar to what we had earlier, except that you only have one extra term. So if I draw the stencil of this scheme, well, let's do that later. So this is explicit. It's very easy to implement on a computer now, because you know the theta values, all of them at n equal to 0, right? So all you have to do is you have to calculate theta at the 1th time. So I can just keep this term on the left hand side, everything else goes on the right hand side, and now I have to simply calculate this for all I comma j values in the interior points. Now boundary points, let us say for now all the boundaries are Dirichlet. You know the theta values as a boundary, so it becomes simple to implement. It's very easy, right? So I'll the next lab problem will be based on this. So for the explicit case, I am not going any further, I won't write the algorithm and so on. It's extremely similar to what we had in 1D. All you have to do is you have to write the update formula using this 2D representation, that's it for explicit. But what about the stability? Now that we have another dimension to look for in addition to truncation error, we also have to look at the stability. So what about stability? Well, now you have the framework available to evaluate the stability of the scheme. We did that for 1D problem in the last lecture, and that was for forward time center space. So now what you can do is, I will give it as a homework now for you to test the stability for this forward time center space scheme for 2D transient heat conduction. So it is slightly different from what we got last time. Last time what we saw was gamma was less than equal to half for the explicit scheme to be stable. But this time, since we have a delta x and a delta y, which may not be the same, because if you have a different size in x direction and different size in y direction, you may want to keep delta x and delta y different for different reasons. So if they are different, then they will be gamma defined for a delta x and gamma defined for a delta y. So when you follow this, the steps are exactly the same as what we did last time, except that you will have more number of terms to look for. So the stability criteria you will get, or you should get, is gamma x plus gamma y should be less than equal to half. Instead of gamma less than equal to half, you have the sum of the two gammas in two directions less than equal to half. Okay. And what we notice here is that the stability criteria for 2 dimensions is more stringent as compared to stability for 1 dimension, right? The idea being that, let's say for discussion here, that delta x and delta y were the same. So gamma x plus gamma y would be if delta x and delta y were the same, just for argument, just to show things quickly. So that means alpha delta t by delta x squared is less than equal to 1 by 4. So what that means is, for the same spatial grid size, your delta t requirement, the maximum delta t you can have, is actually smaller in 2 dimensions, right? So if we write a program for 1 dimension and extrapolate or expand it to 2 or 3 dimensions later, we have to be careful that the stability criteria would change. So sometimes we do that when we write programs, we write it for 1 dimension and then we expand it to 2 or 3 dimensions. But when you are doing that, to remember that the stability criteria will change. So the delta t has to be modified to ensure that the forward time center space scheme is still stable numerically. Okay. So that's all for forward time center space. Stability done. Truncation error, for now we already have an intuition that it's center in space. So that means its order delta x squared and delta y squared, and it's forward in time, so it's delta t. Now this is completely based on my intuition, because I already know that for forward difference and backward difference I get an order delta x scheme. So if it's forward in time, it's order delta t, and for spatial directions, both of them, it's center space, so it's order delta x squared and delta y squared. Again, as I promised that I'll give you a homework sheet where you can try these things yourself. But actually there is more to that. If I do a simple Taylor series expansion and try to figure it out for these problems where you have multiple spatial dimensions and a time dimension as well, you may not be able to do a correct truncation error analysis, because what happens is that sometimes the terms cancel, and we'll see it later in a lecture on modified equation, where we'll see that sometimes terms will cancel in a naive truncation error analysis that we have learned for one dimension till now may not always work. Okay, so we'll have one dedicated lecture on these truncation error analysis for higher dimension equation. That's the reason I am postponing this discussion for future. Okay. So once you go through that lecture, you'll have complete confidence as to how to do a truncation error analysis for problems which have a time dimension and more than one spatial dimensions. Okay. So let's move on to backward time center space. Forward time center space is done. It's much easy to implement on a computer. We know the stability criteria. So let's look at backward time center space, because backward time center space can become useful. As we discussed last time, that because of stability, the time step size can sometimes become prohibitively small, so that you may need extremely large number of time steps, which can make it computationally very slow. So in that case, backward time center space or implicit schemes can become very useful. So let's work on that. So let's write the governing difference equation for backward time center space. So this time on the right hand side, all the thetas are at the n plus 1th time. So I can just move around the terms and write it in a different way in terms of gamma. right? So I simply multiplied the right hand side by delta t. So alpha delta t by delta x squared becomes gamma x, and alpha delta t by delta y squared becomes gamma y. So the only coefficients I have in this equation are gamma x and gamma y. So on the left hand side all the unknown terms are there, right hand side all the known terms are there. So this is a linear equation. The unknowns are, for the n plus 1th time, I comma j, I minus 1 comma j, I plus 1 comma j, I comma j minus 1, and I comma j plus 1 at the n plus 1th time. So all unknowns. So the stencil becomes like this. So stencil helps us figure out which points talk to each other. So in this case, it's these 5 points which are talking to each other through this equation. Now of course I cannot solve this equation by itself like an explicit scheme, because you have one equation and 5 unknowns here, so you need more equations. So for that I have to write this equation. So this equation has been written for I comma j. If you change your point I comma j, you get different equations, you get different 5 terms in the equations. Okay, so you have to write it for all the interior points, and that gives you a system of linear equations which has an equal number of unknowns and equations. So you can solve that. It's very similar to what we did in the elliptic problem or the 1D backward time center space problem, where you got a tri-diagonal matrix that you could solve using TDMA, right? But there is an issue here. Can somebody highlight how what kind of problem will I face if I want to write a matrix equation for this implicit problem? So think about it. But time was not giving you any information in the matrix. Time was, so in transient 1D heat conduction, when we are going from nth time to n plus 1th time step, we got a TDM tri-diagonal matrix system, right? So there was no time in the matrix. The matrix, the unknown was a list of a vector of all theta values along the spatial points. Okay. But here the problem is that it's not one dimension, it's 2 dimension. So you have lots of thetas both along x and y directions. So because theta has to be written as a vector. Ultimately we want a system like this, where this is your theta vector, all the unknowns. In this vector all you have is all the unknowns, but the unknowns are in a 2-dimensional grid now. So how do I write them in a single list, in a single vector? So we have to come up with some sort of a mapping from 2 indices to 1 index. That will allow me to write, because ultimately I have to convert the equations that I have into a linear system, and the way you do that is you write all the equations and then you try to convert that. So the coefficients of each equation, equation number 1 go in as the coefficients in the matrix and so on. Okay. So this is for now, for me this is one equation, there is no time complexity here. I am just trying to solve this equation for once. So given that I know the theta values at the nth time, at the right hand side, I want to solve for theta for the n plus 1th time, that is on the left hand side, and then I will run this loop again and again and again to march in time. So in this case, the index I varies between 0 and n, like in one dimension. So 0 is for the left boundary and n is for the right boundary. Similarly, j would go from 0 to m. We're keeping different maximum indexing because the number of grid lines in the x and y directions could be different. So what I can do is I can start counting from the left and then go to the right and then start moving up. So what that means is, if you look at this figure, I start with zoom into it. I start with the bottom left point and I call this index number 1 for a single index. Then it becomes 2, 3, 4, 5 and so on. I go all the way to n, and then when I go up, this becomes n plus 1 and so on, right? So this would become 2n plus 2, and then we'll keep counting. So we'll count from left to right, bottom to top. So that can allow me to write the theta values or refer to them using single index. That will help me to write a vector of unknowns. So I'll define a single index L, which is the x index I value, because we are counting from left to right. But since if we have gone up a couple of rows, so we will multiply that by n plus 1 times j. Was that wrong? Should that be 2n? Right, sorry. Yes. So it's n and n, 2n, of course. Thanks for correcting. So we can use this update formula to check. So if we are in the second column, which is j equal to j starts with 0, so then j is equal to 1 in the second row, j is equal to 1, so 1 times n plus 1, so that takes care of those n plus 1 points in the bottom row, and then the index I counted from the left. Okay. So now what I am doing is I am writing this governing difference equation in single index. So I comma j minus 1. So let's do one thing. Since I comma j is some arbitrary point, we will write the term theta n plus 1 L for this I comma jth point. So this point that I had around which I am writing the differential equation. So for that I will call it theta L. You have to keep it arbitrary, right? Then L can change values and then you can write the equation for each and every interior point. So then what happens is I comma j minus 1 becomes 1 point below that point. So the coordinate would be L minus n minus 1, right? and for this I minus 1 comma j, which is 1 point to the left, the coordinate would be just 1 less than L, so L minus 1. So for the right point I plus 1 comma j, it becomes L plus 1. Any problems? I think the problem occurred because this starts from 0. That's how we are indexing it. So actually we have n plus 1 points. That's the reason probably I had written 2n plus 1. So you have a total of n plus 1 points in one direction in the grid, in the x direction. So then that's the reason we have to subtract n plus 1 to go from one row to the other. So this actually would have been 2n plus 2 only, right? Because you have n plus 1 points and then n plus 1 points, but since you are starting from 0, so this becomes 2n plus 1. You can figure it out, just calmly check. Yeah, it should be 2n plus 1 because the total number of points we have is n plus 1 and n plus 1, so 2n plus 2, but since we are starting from 0, so it becomes 2n plus 1. I think this time we are correct. Again, actually what happens is if you, depending on the programming language, now earlier I had prepared notes for Fortran, and Fortran things start from 1. So there are different languages depending on which language you use, the indexing will start either from a 0 or from a 1. So if you start from a 0 like in Python, then the indexing becomes different. So we have to be careful which programming language you are programming it in, and then you write the discrete equations, the indexing accordingly. Although you can go from one to the other, but there are sometimes we can make mistakes. It's always good to write everything either starting from a 0 or starting from a 1. Don't mix them up, otherwise you make mistakes like I did. Right, so this is the governing difference equation. So now I can write it in a matrix form comfortably because I only have one index for theta. So I can write my theta as a vector. So can anybody figure out how will the A matrix look like? So right hand side actually is simple, it's just the theta at n, so I will write theta at the nth time. So the power, superscript does not mean power, it's only at the time. So theta on the right hand side is at the nth time, and theta on the left hand side in the vector is at the n plus 1th time, the unknowns. The right hand side could be anything, it's just that incidentally it came out to be theta. What about the matrix? How would it look? Would it be tridiagonal this time? Or would it be different? The easiest way is you write it for an arbitrary equation, so for Lth equation, right? So let's say you have theta L at the n plus 1th time here. So the coefficient for theta L is 1 plus 2 gamma x plus 2 gamma y. That's a diagonal term because you are writing the equation for the Lth. So let's say this is a diagonal term, and then you have theta L plus 1. That is one point to the right, the next point, the next unknown, that will be a coefficient to its right. Then you have theta L minus 1, but you also have theta L minus n minus 1, that will be somewhere here. So what will happen is the coefficient will appear somewhere here. Similarly, for theta L plus n plus 1, the coefficient will be somewhere here. So what we see is that you will have a diagonal, above diagonal and below diagonal, but then you have a gap. You have zeros and then you have another two bands. So this matrix like this is called a banded matrix. And if we apply Gaussian elimination here, what happens is while you are applying Gaussian elimination, since there are lots of zeros between any non-zero bands. So for example, you have a non-zero value here, then you have all lots of zeros, and you have a non-zero here. But during Gaussian elimination, you end up killing those zeros. So from a sparse matrix like this, where you had only 5 arrays, you end up generating lots of non-zeros in the process. You can try it yourself, check it for standard, a simple banded matrix where you have 3 bands, but you have zeros and then you have another band and then you have zeros and another band on the top. You will see that Gaussian elimination will end up generating zeros. And the main USP of Gaussian elimination here was that we have in this kind of a matrix where you have these only few arrays, you only need to store those arrays. But since we are creating non-zero terms in the process of Gaussian elimination, the process will not be as efficient as expected in the 1D case. Okay? And the greater the value of n, because the difference between the bands is a n. So greater your n plus 1. So greater the n value, which is larger the number of points you have in the x direction, greater the jump between the band here and here, the more inefficient the Gaussian elimination method becomes. So it doesn't work as effectively in 2 dimensions. In 1D you got a tridiagonal matrix, but in 2D you do not get a tridiagonal matrix. You get a matrix which is pentadiagonal, but the problem is that you have it's actually a banded matrix. We don't call it pentadiagonal. Pentadiagonal would actually mean that you have 1, 2, 3, 4, 5 all contiguously, but here we have a jump. So Gaussian elimination will not work for us. Well, you can use it, but it's not as effective as in 1D. So this allows us to discuss iterative methods now, which are what you will see any commercial or an open source software in CFD will be using to solve linear systems. Are there any questions till this point? So the backward time center space for transient 2D heat conduction problem, the first problem that appeared was that the indexing was 2D in space. So we had to map a 2D indexing to a 1D indexing, or a double index to a single index, that allowed us to write the matrix form. But the matrix form was such that we could not solve the equation efficiently using a tridiagonal matrix or a Gaussian elimination in general, because Gaussian elimination results in a very expensive algorithm in this case. So now what we are doing is we are looking for a different method to solve the matrix system. The matrix system is still there, or not a matrix system, but to solve this discrete equation. So, since we are defining proposing a new method to solve the equations which are implicit, we will also take benefit of the fact that we will not be needed to write a single index. We will work with double index only, I comma j, because I comma j, when you see that, you can easily locate the point on a 2D grid, right. So, I will tell you the benefits of the method before we actually propose it. So, we do not need to solve a matrix system. So, we will not be solving Ax equal to B actually, we will be using a different technique, but we will still end up getting the solution to the system of equations. I should not say solve, because that is a bit confusing, to write a matrix system, and the other is that we can still work with double index. Right. So, although I said that I do not need to write the matrix system, but to discuss this iterative methods, I will write a matrix system, but you will see that you do not need to write it specifically, but it is good to show the matrix system, because that helps in understanding the numerical analysis for the method. And this time we are basically discussing how to solve a system of linear equations. So, I will not use theta as the unknown, I will use x as the unknown, because typically you write the linear system as Ax equal to B. So, the equations you have, let us say, are A11 x1 plus A12 x2 plus dot dot dot, and then we have A1n xn equal to B1. Okay. Similarly, you will have coefficient still a n n. So, I will write an arbitrary equation, the pth equation. So, a p1 x1 plus a p2 x2 plus there will be a diagonal term a p p x p, and then we have the last term a p n x n equal to b p, and then so on. So, we have a total of n equation, capital N equations here that I want to solve, but this time I do not want to use Gaussian elimination, I want to use an iterative technique. So, I will not write the algorithm right now, because we are out of time. We will just write the idea of, have you learnt about iterative technique or numerical methods in the first year mathematics course, undergraduates? No? Have you heard of the Jacobi method? Yes? Where is that? ऐसे पढ़ लिया. Others have learned it in different courses. Okay. Right. Well, if you have done a course in numerical methods or numerical analysis, you will know that anyways. So, the idea of iterative methods is, you start with a guess. Okay, you have a vector of unknowns here, you guess it, anything, maybe guess all of them to be 0, the whole vector of unknowns to be 0, it is a guess, right, and then you sequentially correct it. So, you go through different iterations. I should say improve the guess. Okay. So, you start with an old values, and then you get a new set of values through some through some sort of an idea that using these equations you will be able to improve upon the values of x. It may not be the correct one. It may not be the one which actually satisfies this whole linear system, but we improve it, and then you check. Okay. I am writing very hand wavy here that the error which is between the difference between new and old. I'll tell you what the error actually, how do you quantify the error, but then we check the error, that is, if the change from one iteration to the other, from old to new, was it small or large. If it is greater than some epsilon that you have chosen, then, so if this error is small, you check for that. If no, so we started with a guess, you got an x old, you improve it, improve old x, you get a new x vector. You check if the error is small. If the error is not small, you start again, this time you make the current new values as old and then you improve it further. So basically you keep improving it until the difference becomes so small that the error becomes almost 0, and that's when we call the iterative scheme has converged. And then if you put those values in the equation on the top, you will see they will satisfy the linear system. Again, this is a very general idea of this method. We will write the algorithm, we will discuss it, under what condition it works, under what condition it does not work, and so on in more detail in the next lecture. Okay.